Hi, this is Dr. Praveen Kumar Kaushik and I welcome you all in OM learning classes. In this lecture, we have discussion about synchronous demodulator for demodulation of AM signals. So as per the previous lecture, we already covered envelope detector, Kerala detector, rectifier detector. As per the basic fundamental of AM modulation scheme, if the modulation index is less than or equal to 1, then the cost effective and simple detector is envelope detector. And in AM broadcasting system, we are utilizing the envelope detector with the property of simple in design and it make the cost effective receiver. But if the modulation index becomes greater than 1, then there is case of over modulation. But by utilizing synchronous detector at the receiver end, we can recover the signal instead of depending upon the modulation index. So, my dear friends, the synchronous detector for demodulation of AM signal is utilized because in the synchronous detector, similar to suppressed carrier modulation scheme, we generate a signal from local oscillator and that signal is synchronous in frequency and phase with respect to transmitted carrier wave. And by utilizing this property of coherency in phase and frequency of local oscillator signal at the receiver end with respect to transmitted carrier wave signal, then this detector is known as synchronous detector. In the synchronous detector, the received signal is there and that is our AM modulated wave. And by utilizing local oscillator, we generate local oscillator signal that is CT. This CT signal is synchronized in terms of frequency and phase with respect to transmitted carrier wave. And by utilizing product modulator and low pass filter, we can get the estimate of our modulating signal, that is our desired baseband signal. So as per the mathematics, we have AM modulated received signal and that is equal to AC bracket start 1 plus KA into MT bracket close into cos omega CT. Then we have the local oscillator signal that is CT AC cos 2 pi FCT. And by utilizing product modulator, we have the product of both signal. Then the term DC is blocked by the capacitor and by utilizing low pass filter, the component that are centered at omega C to omega C are easily filter out. And after low pass filter, we get our output signal that is our desired baseband signal that is equal to AC square into KA into MT divided by 2 and where MT is our desired baseband signal. So as per the utility of local oscillator at the receiver end, the receiver become expensive and complex and the utility of local oscillator that generate a signal which is coherent or synchronized in frequency and phase with respect to transmitted carrier wave, and this method of recovery of modulating signal is known as synchronous or homodyne or coherent detector. So if we observe the advantage of synchronous detector for demodulation of AM signal, then the quality of the recovered message at the output of detector is very high, and there is less noise effect on the detected output signal. And the additional requirement of local oscillator signal makes the receiver expensive and complex. And this is the major drawback of synchronous detector. In similar to suppressed carrier modulation scheme, if the phase and the frequency of the local oscillator signal at the synchronous detector is not coherent in terms of frequency and phase with respect to transmitted carrier wave, then the phase and frequency error occur, and these frequency and phase error results the distortion and attenuation in the detected output. So for doing the consideration of phase and frequency error, we have the mathematical representation as, in this we have the received signal, which is our AM modulated signal. Then we have the local oscillator signal, and this local oscillator signal have delta omega frequency error and phi is the phase error. And by utilizing the product modulator and low pass filter, we have the output EDT, which is equal to H square into Ka into Mt into cos delta omega t plus phi by 2, where the delta omega corresponding to frequency error and phi corresponding to phase error. And this slow time varying function distorts the message signal at the output of synchronous detector. In similar to suppressed carrier modulation scheme, we have 4 cases. In the first case, when there is no frequency error, no phase error, then at the output we have our desired signal that is free from the distortion as well as attenuation. In the second case, there is no frequency error but the phase error is present, and due to phase error, the term cos phi is additional term with respect to our desired signal. And in the cos phi is our time independent and it will create the attenuation in our signal. Again, there is also quadrature null effect. In the quadrature null effect, if the phase error is become 90 degree, then our detected signal at the output of synchronous detector becomes equal to 0. So due to phase quadrature, in the phase error, the quadrature null effect takes place. Now we have the another case in which the frequency error is present and the phase error is equal to 0. Then the cos delta omega t terms is also present with respect to our desired signal. And this cos delta omega t is our time dependent and it will cause the distortion in the detected output. And the amplitude fluctuation at a rate of delta omega, which is known as warble, is also takes place. Now we have the final case in which the frequency and phase error both are present. And here the term cos delta omega t plus phi is present with our desired signal, and this term will produce the attenuation and distortion in the detected output. So as per conclusion, in the demodulation of AM, the basic motive of AM modulation scheme is to make the receiver cost effective and simple. And this is possible only when we utilize the envelope detector at the receiver end. So, as per the fundamental of demodulation of AM signal, we completed all 4 types of demodulator which can be utilized to demodulate the AM signal at the receiver end. So with this, we completed the demodulation of AM signal. In the next lecture, we have canonical representation of linear modulated waves. So thank you very much. Stay healthy and enjoy smart learning. And please subscribe this channel for getting regular updates.